For ROMs, we're going to use, or we can use dot notation, where a dot indicates a 1 being stored. So for example, at address 10, the value 1, 0, 0 is stored. At the address 11, the value 0, 1, 0 is stored. And so cells that contain a 1 basically don't have anything there, and a cell that contains a 0 has a transistor tied to ground. So that when the word line goes high, right, when this word line goes high, it's going to pull this bit line down to this, in this case, data bit 1 down to 0. It's going to pull that right here. If we draw it here, and that word line goes high, it's going to then pull that bit line down to 0. And where there's a 1 here, there's nothing there. So when the word line goes high, that line just stays at 1 instead of getting pulled down to 0. So here's the storage 0, 1, 0. At address 10, we have 1, 0, 0, and so forth. And we still, just like all memories, we have the depth, in this case 2 to the 2 or 4 words by the width, the word size, 3 bits. Fujio Masuoka developed memories and high-speed circuits at Toshiba, and he invented flash memory as an unauthorized project, which he did on nights and weekends. The process of erasing the memory reminded him of a flash camera, so that's why he named it flash memory. But unfortunately, Toshiba was slow to commercialize the idea, and Intel was the first to market in 1988. And it's grown, immensely. We all have at least, several, if not, dozens of flash memory devices, that we use regularly. So one thing we can do with memory arrays is we can actually perform logic with them. And it turns out, we'll talk about this later, this is how logic, field programmable gate arrays work, is they use memories to perform logic. So for example, instead of looking across at 0, 1, 0 being stored there, we can look down at what's being stored for any combination of address bits. So if we, for example, call this A sub 1 and A sub 0, right? Those are our address bits. Well, this data sub 2 is performing the XOR, because we have for the 1, 1 input and the 0, 0 input, we have 0, and for the 1, 0, 0, 1 input, we have 1s. So we have data sub 2 actually performs the XOR of A1 and A0. So data 2 equals A1 XOR A0. And similarly, we can look at data sub 0, for example, and that performs A1 and A0. Or we can have this one where we get, this is equal to, well, it's 0 then, so data sub 1 equals A1 A0 bar, which is equal to A1 bar or A0. So it's going to output a 1 when we have A1 bar. So here's A1 bar. There's our 1s. Or A sub 0. And here's the A1 bar. So we can think of our memory arrays performing logic. And that's useful because, well, just depending on what bits we store, we can perform different functions. So now let's use our ROM, a 2 to 2 by 3-bit ROM, to perform these logic functions here on the left. So we'll put X, Y, and Z, tie them to our bit lines, and put A and B on our address lines. And so we want to make X equal to A and B. Okay, so we'll put a 1 in that bit. y equals a or b. So y, we want to have a 1 when a is true or when b is true. And z equals a and b bar. So z would only have a true output when a is true and b is low. And so we could still think about this as our values being stored at our various addresses. At address 0 would have the value 0, 0, 0 stored. Address 1 would have 0, 1, 0. Address 2, 0, 1, 1. And address 3, 1, 1, 0. But now we're using this memory to perform logic for our different outputs. So x equals a and b and all those different functions. So we can look at this and say, well, what is this memory array? What functions does it perform? Well, data sub 2 is performing a sub 1 XOR a sub 0. Look at that function. Data sub 1 is performing, well, this is the same as we had before, is performing a sub 1 or a sub 0 bar. This is that function. And then finally, our last one, 0, 0, 1, data sub 0 is a 1 bar and a 0 bar. Okay, this is our single one, is when a and b, a sub 1 and a sub 0 are both low. So we could implement the following logic functions using actually any memory array. So DRAM, SRAM, or ROM, just depending on what bits we're storing. So x equals a and b. Well, here's our x. We connect our address inputs to a and b, and we get 1, 0, 0, 0. This is written with 0 on the bottom. And then we could do our next one, y equals a or b. Well, that would be 1, 1, 1, 0. This is written, upside down from a truth table. And then last one, z equals a and b bar. That would be this one. The rest are going to be zeros. And so the main thing here is that we can perform logic with our memory arrays. And these logic arrays, these memory arrays that we use to perform logic have a special name called lookup tables. So we can look up the output for each input. So it's basically a truth table in our memory, right? So in this case, we're doing the AND operation. Here's the lookup table. We connect our input variables a and b to the address inputs, and then our memory acts as a lookup table for our truth table. And let's say in this case, we're doing an AND operation of a and b, and we said, oh, actually I meant to do the, the OR operation. So now I just changed the value that's stored in my memory, and it's now an OR gate instead of an AND gate. And so this reconfigurability is the feature that we're going to use to with our lookup tables or our memory arrays used for logic.